doping is an important process to control the electrical characteristics of semiconductor by adding up the impurities. Later on, you see that you can also control the mechanical properties, and most importantly, you can control the etching characteristics against some kind of etchant. In other words, if you have a doped volume, doped area, doped shape on top of the wafer, you can leave such area from the etching. You can protect such area from the etching. That really means that you can come up with various kind of shapes. So it is important to design the doping process. It is important to design the recipe so that we can control the concentration of the doping and the doping profile and the depth. Okay. So let me talk just a little bit more about this kind of cases. So compared with the constant source at the surface, we can control the amount of source at the surface. It's called the limited source case. Okay, in this case, the doping occurs in two-step process. First of all, deposition of the impurities right all over the surface, and then driving this deposition using a thermal process. That's a diffusion process. That's what you guys saw last time when you had a tour in the clean room. When you looked at the furnace, one of the furnace they used was actually drive-in furnace. And in this case, you would actually provide certain known dose on the surface, and followed by driving. So that dose is a total integral amount of concentration. You have certain amount of volume and depth, and the concentration and the area. Then you can calculate such amount of total dose. We call such amount dose. Okay. In that case, if you solve the doping equation that we derived last time using similarity variable, you can easily solve it. It will be part of your homework and your report, your exam as well. This is the concentration you can obtain out of this pre-known dose Q. And as you can see here, the function itself is a combination of spatial coordinate system, and the time is exponential function. However, the number that is multiplied in the front is actually also the function of time, which really means that as time goes by, this number will be reduced. That really makes sense because we supply predefined amount of dose over the surface, and as time goes by, such dose will become less and less, because these impurities will diffuse into the body of crystal silicon. So that's what's happening right here. And what is really important is, in that case, we would like to know when and where this doping concentration becomes the same as the background concentration. As I said, the wafers we obtain has some kind of lightly doped impurities, p-type or n-type. Okay, so whenever n-type impurity concentration becomes the same as p-type background concentration of the p-type wafer, in that case we create NP junction right there. Okay, and there are a lot of things you can do with this NP junction. You can come up with the diode, you can come up with the bipolar junction transistors, you can come up with solar cells as well. So it's very interesting interface with it. So if you equate these two, you can easily calculate, junction depth, the space coordinate where this number becomes the same. You can easily calculate this concept. Maximum impurity concentration. Well, we had some good discussion throughout the class. So there are a number of the concentration, impurity concentration, maximum concentration is limited by the precipitation of these impurities. In other words, if you provide more dopant than this maximum concentration, then the surplus amount will be just precipitated. You cannot, put this amount into the crystal anymore, and this is really useful curve. Why do you need such a why do we need to know the limit of this the maximum concentration? That's because we want to have high concentration doping area. Why? Because whenever you dope certain area with high concentration, whenever you dope certain volume with a high concentration, such body of doped volume will be resistant against certain chemical etching, so that you can create very interesting island of this the etched shape. So this is the really doping probably this exponential function. So it'll look pretty much like a Gaussian distribution in this sense. So this graph will come down and then go down to 0. Not like this actually. And the number multiplied in front will decrease as time goes by, which really makes sense, And there's a background concentration. So this is typical response you can obtain out of this doping process. So junction depth is a depth where this doped concentration, for example here p-type Gaussian distribution, boron doped, and n-type, for example, silicon background, the phosphorus, for example, is a background concentration. It is the depth at which these two concentration becomes the same, and you can easily calculate, this depth. So at this depth, you really calculate, if you consider this background concentration all together, the total doping profile will pretty much look like this, right? So at this point, p-type impurities, n-type impurities becomes equal to each other. So you will obtain the pure semiconductor. That is p-n junction. It's right here. Okay, so that's the profile you can obtain. One of the furnaces you guys saw when you had a tour, when I had a tour myself in the clean room last time, was called Pockle furnace. Well, it is one of the ways of trying this doping. Okay, in that case, people use such furnace for doping phosphorus. Okay, and this classical method, it's not used in our clean room anymore, but it's a very good method because you can create many the doping on many wafers at once. It's targeted for production process. So phosphorus doping, we use diffusion furnace. We call this bubbler. You'll see why this is called bubbler soon. The chemistry of this doping is phosphorus pentaoxide, P2O5 is the chemical we use. It's a toxic chemical. It's very toxic chemical. And we make it react with 5 silicon atoms, leaving phosphorus atoms right here, and silicon dioxide. Of course, so after this doping process, you will obtain some oxide. You have to remove the oxide. And then this silicon, how do you get this phosphorus pentaoxide? The original chemical, the supply chemical you use will be POCl3, phosphorus oxide trichloride. Okay, and we call this Pockle. Okay, Pockle. It looks like Pockle, right? And Pockle react with the oxygen. You can supply the oxygen. That produces this phosphorus pentaoxide and chlorine. So this is really toxic process, and it's a really hazardous chemical. So they got MSDS, Material Safety Data Sheet, and you have to read this Material Safety Data Sheet and understand the danger and the measure against this danger as well. So you need to be very careful about it. So in clean room, we have a lot of measures. We have a lot of sensors, detectors that can actually detect and then maybe shut down the clean room in case there's a leakage. So it's a really important process. So this is the furnace we saw last time. It is the crystal, the quartz furnace. We have a boat where you locate your wafer, and here are lines of gas supply. Normally, people will let the nitrogen gas flow, so that nitrogen gas is a non-reacting gas. There's no reaction when this nitrogen is provided. Only the temperature is controlled, and then you switch to oxygen. Look, what happens to this oxygen? Well, nitrogen, just turn it off and the nitrogen will bubble up. This liquid source of cocoa will evaporate and react with oxygen together to create phosphorus pentioxide, and that will create phosphorus on top of wafer, where from the surface this phosphorus ions will diffuse into the body crystal lattice of silicon because of the high temperature effect, diffusion process. And the remaining the gas, which is very toxic, chlorine gas, will be actually burned out and then just released into the other places. So this we call this scrubber, actually, scrubber. Okay. So this is a process typically used in industry to create the wafer in many copies of this doped surface. Okay. And in our clean room, we don't use it. It's very dangerous. And we use different method, which we'll talk about. That is the ion implantation. Ion implantation. You guys saw this machine last time, right? And it's a really nice machine. You know, there's a lot of quantum mechanical knowledge involved in this whole process. So what you have is you have a source, like a gas, that produces that has some elements of phosphorus, or some elements of boron, maybe some elements of arsenic. These are all toxic chemicals, and that goes through the ionizer, so that this whole gas will be ionized, creating the impurity ions. And these impurity ions will look like a current, and they can be controlled by the magnetic circuit. You know, because you know, this magnetic current relation. You have a current and you know, magnetic field. Then the force will be 90 degrees about this treble, so that you can control this treble, and you can use some electrostatic aperture, which can focus these ions as a beam and then make them accelerated using electrostatic forces. You know, let them travel faster and faster by using electric field. So it's like a very interesting physics experimental apparatus which can be used for the production of semiconductor. Isn't that nice? You know? So that again you have a focus mechanism, and then the control beam area. Well, in this case, the neutral elements will be separated out and then removed. It is only the ionic components, which is basically P plus or B plus, you know, the B minus, the impurities, and you can scan them like a TV set, the old TV set, the vacuum tube, where they use this electromagnetic lens to steer the travel course of this electron, of these charges, boron charges and phosphorus charges, so that you can scan, you can draw the line, so that you can actually scatter the ions over the surface more or less uniform. That's what they do there. And you have a target here. It's a wafer, basically. And the wafer is grounded, so that it can absorb these ions. You know, so it's a very interesting machine. You saw that it's a huge machine to protect everything from the high electrical interference, and you maintain the vacuum temperature. Amazingly, is a room temperature. You don't have to elevate the temperature of the wafer. So that's for the initial deposition, right? At room temperature, and then you elevate the temperature of the wafer to broaden this doped area. That's what they do. So initial doping would be Gaussian. Look, this is initial condition. Okay, when you solve partial differential equation, this is a very special initial condition because this initial condition is like a Gaussian distribution. Look, you have a peak distribution right here from certain depth from the surface of the wafer. Okay, and then you have an exponential function right here, and RP is the distance where this peak distribution occurs. So it's like average distance. Why is considered Gaussian distribution? Quantum mechanically, when you shoot these little particles over the surface, there's statistics involved, right? And statistics tells us that the distribution of these little elements, little atoms, little impurities will be well scattered, like a Gaussian distribution. That's what they use in quantum mechanics. Everything is a statistical, function. So it's a statistical function, and RP is again the mean value of this scatter, and delta RP, and delta RP is deviation. You can calculate this deviation using the knowledge of statistics, right? And that's the deviation you have, exactly like that. And in semiconductor business, we use special names on this. RP is called projected range. It's projected range indeed, right? The mean value of this doping. NP, peak concentration at a projected range. And delta RP, straggle, deviation, how broad this doping is actually. Okay, if you have a very large value of delta RP, really your Gaussian distribution is broad. On the other hand, if this is small, then you have very sharp distribution. And those amount is somewhere between 10 to the 10th to 10 to the 18th power of impurities per square centimeter. Why is not cc? Because it's a dose. What did I talk about the dose? It's an integral value along the depth of this doping profile. Okay, so if you integrate the whole volume cc with the depth, you're going to obtain the area. That's going to be centimeter square, right? So you just integrate from surface to the body of silicon on this whole doping, right? And you're going to obtain this dose, square root 2 pi NP, the maximum doping concentration times delta P. Look, the wider the delta P you have, the larger the delta P you have, the more the doping dose you will have, which makes sense because you will provide more distribution. Okay, and interestingly enough, this result of the ion implantation, I don't know if you can see it, it's identical for silicon dioxide and silicon. Yeah, that's the deal. So you have certain thickness of silicon dioxide. You can use it as a protector for this doping, but again, there's a penetration occurs. So you need to have a certain thickness to maintain to protect silicon surface from being doped by this ion implanter. Well, these graphs are experimental data, which means that this characteristic depends upon the equipment you use. That's what we discussed in front of the ion implanter we have. currently in our clean room. So you need to obtain these graphs from a particular machine. Okay, so these are just examples of this doping characteristic, the ion implant characteristic, based on experiments using specific equipment. Okay, so for this particular equipment, they mentioned in this reference book, project range, RP, remember the depth at which the maximum concentration occurs is a function of acceleration energy, kilo electron volt, right? What is 1 electron volt? It is the energy used to accelerate one single electron over the course of 1 meter of distance, right? Yeah. So if you have, for example, 100 keV, like the number we saw last time, is typical number they use in our clean room as well, 100 kilo EV. And if you want to do phosphorus, example here, projected range will be slightly more than 0.1 microns. That's the question I had. I asked to the TA. He couldn't answer because he's just an operator. But if you actually want to design your own process, you need to know this number actually. So 0.1 micron, that's 100 nanometers, pretty deep actually. So from the surface down to 100 nanometers is the peak distribution that will occur, you know. And that depends upon what kind of the impurities you have. Boron, for example, is even larger, 0.1, 0.2, 0.3. About 300 nanometers deep into the silicon crystal. However, if you use low energy, of course, such penetration would not be very deep. Okay, that's something you need to consider. And struggle as well. This is the struggle, delta P. The deviation that depends upon the acceleration energy as well, and it is more or less proportional to the acceleration energy. That really makes sense because you shoot your atoms, your ions at a high velocity, and there are bigger chances of these ions to scattered, at the target, basically. So that really makes sense. You can even calculate all these kind of things. That's what your friends are doing in the Department of Physics, right? They use quantum mechanical calculation to look at these kind of things. Well, and then after this, you would like to drive in this profile. Basically, this profile is too sharp, too shallow, too thin sometimes. You want to make it broaden towards the surface, broaden towards the body of this wafer so that you can create some reasonable amount of volume where you can control the electrical properties, mechanical properties, and the etching characteristics as well. So in that case, you need to make this broaden, and this peak distribution will go down, and this will become broader and broader, right? That's what will happen, and we can calculate it as well, right? So this process is called annealing process. There's a very interesting things. If I have all these things, okay. Very interesting characteristics you need to think about. We are dealing with this single crystal silicon. Okay, so this is the model of such crystal lattice, represented by these bars and balls, all plastics, right? First of all, when you try the doping over the wafer, many cases people use 110 wafer. What is 110? You will see it pretty soon, because we're going to study the crystallography. 110 wafer. 110 is this direction. Can you see that? You see the big hole. Actually, it's the biggest hole that you can find out of this crystal. Okay. You see my eyes, my eye right here. You know? Okay. And think about it. You accelerate the ion and then shoot through this hole. Okay. What will happen if the direction of shooting and the direction of this hole, 110 direction, is perfectly aligned? Well, there will be very interesting phenomena that's occurring. These little particles, the ions, will penetrate very, very, very deep into the silicon, because there's nothing that blocks this penetration. In that case, you won't be able to obtain nice distribution. Everything is just random, more random, and the depth of distribution occurs at a very long length indeed. So in order to avoid such kind of problem, let this particle hit the lattice and then scatter nicely and form this nice Gaussian distribution. They will tilt the wafer a little bit. So not like this perfect orientation, but tilt a little bit. In that case, the atoms, the impurity ions that are accelerated will have a good chance of hitting this the lattice, right? And then scatter around. Now, the event that will happen in that case, look, there's a high energy atoms that will hit the lattice. Well, what I'm saying here is all can be modeled and simulated using quantum mechanical knowledge. Okay, so it's just a simple description of it. Well, when these atoms hit the lattice, what will happen? They will break. They will break apart. Okay, look. They'll break like this, right? Lattice will break, and your crystal silicon would not become a single crystal anymore, and we lose all the good characteristics of this single crystal silicon. That's not really good. Okay. So how can you solve this problem? How can you fix it? Well, you will elevate the temperature and allow these broken lattices to align thermally and then form a nice bond with each other again. It's called lattice fixing. Okay, so this high temperature process, annealing at, for example, 1100 degrees Celsius, is necessary to fix the broken lattice damage. Okay, and second, obviously, because you elevate the temperature, the whole distribution will be broadened. Okay, because additional diffusion will occur throughout this process. That's very interesting, indeed, right? All right. So initially, distribution will look like this after ion implantation, and if you introduce annealing process, then distribution will come like this. How can you get this? Again, it will be a part of your homework. You will have to solve the partial equation, but this condition has a initial condition indeed, right? It's initial condition, right? And as time goes by, look, this peak distribution becomes lower and lower, and this straggle square is comparable to 2 times dt. This is amazing, right? Because if you equate these two out, you will be really 2 square root dt. That's the number we already know. Why is it 2 square root dt? So I have this. Look, It's not square root 2, it's a 2. Because of 2 here and 2 here. So if you just take the square root of 4, you'll have 2. Okay, that's the number we had, right? Last time. Remember, we used eta equals to x over 2 square root dt. So this is comparable to delta rp. That's what I'm saying. Okay. So our model for solving partial differential equation by introducing singularity variable gives us very important meanings of this, physics that's occurring throughout this process. And again, exponential function and RP delta RP will not change, right? The mean value will be there always, and it will become broader and broader following this formula. And because delta RP is actually usually very small compared with the dt, which is diffusion distance. Diffusion occurs along a long distance, and the straggle is just as small, right? So initially it's a very narrow bandit, but becomes broader and broader bandit. And in that case, delta RP can be ignored, and you can make the equation neater. It's neat. It's very simple equation, right? And again, this will look pretty much like the pre-deposited doping condition. And that's very interesting. Okay. All right. So the beauty of this ion implantation is we can mask out the area. In other words, we can try selective doping. We just have a thick film and then opening, and then whenever there's an opening, such an opened area, opened shape will be exposed to this bombardment of impurities. So you can control the shape of your devices. That really means that we can come up with very interesting shapes that you will see later on, that is used for a variety of sensors and also for medical devices and neural implant as well. And that gives us very nice tool for biological experiments. And I think that in the future there will be more valuable tools that can be used for these biological experiments, because the size scale we are talking about is very small. It's multi-scale, right? Ranges from millimeters down to microns, nowadays nanometers, in a production-oriented way. And this chance has never been possible, not even with nanotechnology. This is not nanotechnology, this is the semiconductor technology that has been existing over 50 years. Now we have a first chance to create these little devices at the scale that's comparable to single molecule, okay? Even smaller than the proteins. Proteins are the range of 10 to 100 nanometers. And we are talking about 1 nanometer scale, okay? DNA, for example. So in the future, probably you guys will have a chance to come up with such kind of devices, and then try unprecedented biological experiment, which is the first chance, I believe, which has never been done yet, actually. Well, so that's the beauty of this selective mask process. So mask materials people use is oxide. The number in the parenthesis is the amount of doping penetration compared with silicon. Silicon oxide, same, 1. Nitride, a little better, 0.85. So it has more blocking capacity, okay? So when the doping depth occurs like 1 nanometer, it will be 0.85 nanometer in the nitride, okay? Photoresist, it's not very good. It's a soft material, so that these accelerated ions can penetrate very well. However, what's good about this photoresist is that you can coat, make it very thick, okay? So that this penetration will stop somewhere in the body of this photoresist. But we can make it bigger. Metal is best. They can block out, almost all this penetration. So that's really nice. Okay. And so minimum oxide thickness, if you want to calculate, for example, minimum oxide thickness, you have to predefine the desired doping concentration at the surface. For example, here you have the doping concentration that you would like to have. Right here, x0, right? And x0, if this is target. Then you would design the thickness of silicon dioxide like this. So how can you obtain this? Well, it's simply the calculation. Well, basically, NX0 is the doping concentration you would like to suppress. You would like to make this doping as small as possible because this is the blocked area. This is the screened area where you would desire that there will be no doping occurring right here. Okay. So if you want to suppress like this, how much? That's an engineering sense. 10 times of the background doping, 100 times. So 10 times smaller than the background doping, 100 times smaller. That's what you decide as an engineer. Well, we'll say 10 times. So the doping concentration at the surface of silicon, you would like to have 10 times smaller than the background doping. You have this equation, and you can solve it right away. And depending upon the peak distribution and the background distribution ratio, this number, the penetration depth x0 can be calculated based on RP, right? And it'll be RP plus n times delta RP. You can summarize into this equation. Please take a look at this equation a little bit more detail. Then this n could be 3 times, 4 times, 6 times, depending upon the peak distribution you have. The larger the peak distribution you want to have, the thicker the material you want to grow. That really makes sense, right? So this is a good way of setting up a reference for your design of this film thickness. Okay. Again, this will be part of your homework and your midterm exam. Right. And you also need to consider the lateral distribution because this scattering not only occurs into the silicon but also along the surface of the silicon because they will scatter out. Okay. In that case, we use delta R orthogonal. Okay. That will be pretty much similar to delta RP right here. Okay, so you have certain kind of distribution inside this doped profile, but then along this mask you have some kind of fringe effect. So you need to consider that as well. That's what this graph really means. So think about it. You have, for example, right here, you have this kind of profile. You cannot really avoid this kind of a fringe effect. Collateral collateral distribution as a result of scattering. Okay, and with this doping, you can create something very, very strange indeed. Look, you have a background concentration like this. For example, N-type wafer, and on the surface of N-type wafer, you would ion implant P-type material like the boron, and look, you will have this kind of a Gaussian distribution as you expected, and every time this background concentration becomes the same as the doped concentration, you would have NP junction. Okay, so really what you have here is that you have NP-N junction. What do you have if you have NP-N junction? Well, transistor, right? So we call this double junction. And a long time ago, like 20, 25, 30 years ago, people paid a lot of attention to this technique. because they can reduce this thickness. And when they reduce this, well, at that time, the patterning technology was not really advanced. You cannot really have a good control of the patterning size. That determines the speed of operation of the transistor. However, this doping is controlled by the chemical process, right? So that you can control the thickness of it. You can make it very thin, in other words, and you can make your device function at a very high speed, super high speed. Even though the overall area is large, this area, we are talking about the depth. Okay? And if you combine the idea of area and depth, if you can reduce them together, that's the modern transistor we are talking about nowadays. So that's a very interesting idea. So you can calculate this depth. Well, I'm pretty much finished with the doping, and we'll move on to the next topic of metallization. Oh, sorry, before the metallization, I think there's one more topic that we need to cover, and that will be furnace. Furnace. Oxidation. Oxidation and acidity. Okay, right here. It's not there yet. Let's use this material. Okay, remember, I talked about conformal deposition, right? And mostly it is highly likely that you can maintain such a conformal deposition if you use LPCVD, low pressure chemical vapor deposition. Why? Because at low pressure, all process is reaction limited compared with the diffusion limited. In that case, gas can diffuse very well into all detailed structure and pretty much cover the whole area. One of the most important processes that we use in that case is polycrystalline silicon. Polycrystalline silicon is pure silicon, semiconductor silicon, but it has the crystal isolated into certain volume, like a grain. Okay, so within a certain grain, it will be a single crystal, but if you jump over to the next grain, it will be single crystal oriented in the other direction. So there will be grain boundaries. That's why we call this polycrystalline silicon. In short, we call it polysilicon. And in shorter term, we call it just a poly. So we say we deposit poly. That really means that we deposit silicon. Turns out that this polycrystalline silicon is at the heart of micro electromechanical devices nowadays. Okay, some of the devices that you use nowadays in your mobile is actually accelerators, or accelerometers, and rate sensors, gyroscopes, and the membranes, and timing devices, and even the camera control, the lens control devices, they are all made with polycrystalline silicons. Did you know that? And so it's very interesting, important mechanical material. So we're studying a lot of, we spend a lot of time studying, designing, mechanical structures out of these polycrystalline silicons. Okay? And in many cases, in CMOS process, polycrystalline silicons are used as the conductor. Of course, it's not better than metals in terms of conductivity. Look, the resistivity is in the range of 0.01 to 0.001 ohm centimeters. And in metals, aluminum for example, we are talking about micro ohms. So this is about 1,000 times worse in terms of conduction. Still, it conducts a current with highly doped materials. So we can use it as a conduction lines. And we have a full control over this doping range. And why can we use this one as mechanical material? Later on you'll see that it has the high etching contrast selectivity. In other words, chemicals like liquid hydrogen fluoride, HF, can etch away silicon dioxide easily. This cannot etch very quickly to polysilicon. So you can leave the polysilicon out of the stack of silicon dioxide. How can we stack them together? How can we combine this process? We're gonna study much more detail later on. That's called surface micromachining. We're gonna study that. And the chemistry of LPCVD is simple. SiH4. What do you call this? Silane gas. Okay, will be a pyrophoric process. Becomes silicon and leaves the hydrogen. So it's a really, again, very dangerous process, explosive. Occurs at temperature range around 600 to 650 degrees Celsius. So remember, the oxidation occurs somewhere between 900 to 12, maybe 1300 degrees Celsius. And silicon nitride deposition, we studied last time, occurs at around 700 to 900 degrees Celsius. And then polysilicon process occurs at around 600 to 650 degrees Celsius. So there are temperature ranges of a specific process. And what's important is that stress condition varies depending upon the temperature history. So it's hard to control the stress, but we can control it. That's why we need engineering process in these cases. And the crystalline structures, if you elevate the temperature, you have more crystals. And that really makes sense because you allow the time for this lattice to align with each other to form larger crystal. But at low temperature, such chances are rare, so that you're going to be ended with so-called amorphous silicon, less crystal-oriented silicon, okay, fine grains in this case. Depending upon the your goals, you can choose different processes. Okay, so look, this is an example. Well, again, this whole curve depends upon the equipment. So you have to run a experiment to find out about this characteristic. That depends upon the temperature. This is deposition temperature, and for instance, this is the pressure at PCVD. We maintain something like 300 millitorr, which is low pressure. And depending upon the pressure and the temperature combination, you're going to be ended with the sometimes tensile silicon, the other time compressive silicon. So you need to be very careful. In case you obtain tensile silicon, that's why we need annealing again. Throughout this annealing process, we can lower the built-in stress as a function of time. Okay. So if you leave your wafer at high temperature, 1000 degrees Celsius, for long enough, you can obtain less stress structures. Okay? That's where we need annealing. So there are a number of different reasons why you need annealing. First of all, you can fix the lattice after ion implantation. You can broaden your diffusion by annealing process, and you can reduce the built-in stress, mechanical stress, by annealing process or the thermal process. How does it occur? Well, you don't want any chemical reaction to occur, so you will just let nitrogen flow into the furnace, but just elevate the temperature. Okay, that's the annealing process. Okay, so people use LPCVD polycrystalline silicon as a conductor, but the best conductor is obviously metal. And we call, if you deposit metal thin film over the surface, because this process, we call such process metallization. Okay. So the goals of metallizations are, first of all, electrical contact with doped silicon. You have a silicon and you want to run a connection between the silicons to the doped area to create CMOS, for example, to provide electrical current, to measure the voltage out of sensors. So there are a lot of different goals, but you need to deal with this current and the voltage. Then you can use this metals. That's interconnects basically, right? You can use them as interconnects. Well, in your homework, in your midterm exam, I will show you certain, I will ask you to come up with some schematics to achieve certain CMOS logical function, AND gate, OR gate, NOR gate, whatever. And I will ask you to design the mask. And basically, what's really important is interconnects, right? From which device to which device you want to connect them together. And in reality, what kind of masks do you need, okay? So these are the things you need to think about. Aluminum is the most popular material because it is easy to deposit and easy to etch. You see how you can deposit, how you can etch. Furthermore, you can reduce the native oxide. Remember, on top of silicon, there's a very thin layer of oxide, right? And if you just deposit metals, you have to have this native oxide be removed. Of course, you can etch them away first, but still, there might be something remaining. But if you deposit aluminum, they will automatically, remove this oxide. That's the beauty of it. And more than anything else, resistivity is one of the lowest resistivity material, which means that it's really conductive, highly conductive. Okay, it's only 3 micro ohm centimeters. What was the typical resistivity you would obtain with the polycrystalline silicon? Well, it's about 1 milliohm centimeters. It's 1,000 times more conductive than polycrystalline silicon. The problem is aluminum can be well attacked by HF, hydrogen fluoride. Why HF is important? Because normally you use HF to create certain movable structure. If you have aluminum on top of it, your aluminum will be removed away. You don't want that to happen, so you need to come up with different combinations. And there's a famous phenomena called junction spiking. Look, right here, what you want to do is you have an N-type area, you have to have aluminum as an interconnect to the other area and silicon opening, right? And when you deposit aluminum will actually penetrate deep into the silicon somehow and create this spike. When you have this spike, this area, 2 areas is short-circuited, useless, and you will screw up the whole device. So this is what happened to the process that your TA is managing now, actually. Okay, suddenly he learned that his device is not working properly as determined and as planned, and he discovered that it is the junction spike that screwed up the function of the whole device. Okay, now he came with a totally different process. So junction spiking is important. And the aluminum has very low melting temperature, 660 degrees Celsius. It's just a melting temperature. Even at 300 degrees Celsius, aluminum will start changing its physical properties. So you have to be really careful about dealing with aluminum whenever you put your wafer into high temperature process. Of course, obviously, if you have your wafer aluminum coated and then put into the oxidation furnace, what will happen? Aluminum will be just melt and evaporated. You will screw up the whole clean room actually. You have to be really careful about it. And reaction temperature, well, again, as I said, as low as from 250 degrees Celsius, aluminum will start reacting with interface materials. So process, sometimes people elevate up to 400 degrees Celsius. If you don't want any physical property change, you don't want to go up to that high temperature, right? Maybe keep below 150 degrees Celsius. Alternative materials, that's why people use polysilicon, even though conductivity is not good. Still, if it's conductive, it's okay for some applications. And people use something called silicide. That is actually the combination of tungsten and aluminum, right? It's a silicon, okay? Semiconductor and metal together, okay? And that creates very interesting material. Well, the way you deposit this metal is called evaporation. Evaporation. You would bombard the metal pellets with high energy ions, basically currents, and make this metal go up to high temperature, at which temperature is so high, so metal will evaporate, okay? Boil and evaporate, basically, But the idea is, whenever this metal evaporates, you would like to maintain the environment at super high vacuum, not high, low pressure. High vacuum, very, very high vacuum. We call it extra high vacuum, okay? And in order to maintain that, you use not only mechanical vacuum, because you see that there is a limit of vacuum you can achieve with mechanical vacuum pump, okay? Whatever pressure you create, there are certain limits which you cannot really go over to achieve certain vacuum. In that case, you need a very special vacuum technology, high vacuum technology, high vacuum pump. You just put them in tandem together and maintain super high vacuum, and then make this crucible with the metal pellets go up to high temperature, and then make this metal evaporate as atoms, and then deposit it over the surface. Why is this possible? Because at very low temperature, very high vacuum, the ions that are evaporated will travel in a straight path. How straight it is, you'll see soon, okay? Well, so the method of evaporation in classical approach, they use something called a thermal evaporator. Basically here, you have a coil around the metal, so you melt the metal, make them evaporate. That's possible. And nowadays people use electron beam, E-beam evaporator. So you have again the electron source right here. You have again the electromagnetic lenses, FBI, and you can control the path of these ions, well, basically electrons, that actually land upon this crucible pellets. Okay, so you can scan X and Y and create certain pattern of the scanning to melt this metal effectively. Right? What's important is that surrounding temperature will not go very high, will not go up very high. You have a cooling water around it, right? So the whole vacuum is, in principle, is maintained at room temperature. Should be maintained at room temperature. Okay. We are talking about the vacuum, and 1 atm is 760 millimeter height of mercury, and this experiment was carried out by Torricelli, right? Italian scientist Torricelli. That's why we call this 760 torr in 1 atm at the standard condition, right? Named after Torricelli.
And that corresponds to 1.013 times 10 to the 5th power Pascal, approximately 100 kilopascal, approximately 100 kilopascal. That corresponds to 14.7 pound per square inch in the English unit. Pound per square inch. Right? That's standard vacuum. The vacuum we want to achieve here is like a beast. 10 to the minus 6 to 10 to the minus 7 torr. Think about it, it's not even milli torr. Okay, so this is super vacuum. And in this case, at this low vacuum, the particles will travel in a very straight path. And the path of one particle to travel before hitting the other particle is called mean free path. That's why we use mean free path of metal atoms. The mean free path of metal atoms becomes very long. How long is it? You'll see that. So that deposition is directional. So the path is like a line of sight, and it prevents oxidation as well. At super low vacuum, there's nothing to react, and there's nothing to trap in the film. Okay? For example, if you just have some impurities existing in the vacuum, well, they will be trapped inside the thin film. That kind of thing does not happen. Problem and advantage at the same time is poor step coverage. Well, sidewall, if you have deposition from the top, can never be able to, would not be covered, would not be deposited. Is that good or bad? Well, sometimes good, sometimes bad. Why is good, why is bad? I'll talk about it. All right. So these are the vacuum technology that can be used. It's not very highly visible. I'll give you guys the material. Well, depending on the vacuum range, we call this rough vacuum. It's gonna be 10 to the 5th Pascal down to 100 Pascal. And medium vacuum, and these are the vacuum that we are talking about for low pressure chemical vapor deposition. And high vacuum is 10 to the minus 7, something like this. That's even ultra high vacuum. Okay, and depending on the vacuum technology, people use mechanical vacuum pump and use diffusion vacuum pump and turbo vacuum pump, cryo pump, many different combination of very special technologies. Okay. So what is mean free path? Well, we can try a rough calculation. The average distance of molecules travel between collision. So in this calculation, you can assume that the collision occurs when the center molecule comes within twice the radius of that central molecule. The other one. That makes sense, right? So this is, typical collision with maximum volume. Okay. Well, so that volume is the average volume that is occupied by one molecule, single molecule. In that case, collision occurs. That's what we think. And that distance we think is lambda bar. Okay, so if you calculate such volume, it will be the volume occupied by single molecule. That's what I said. So volume divided by total number of molecules, and that volume, they are same with each other. So you can calculate lambda in this sense, and you can introduce the ideal gas law. Ideal gas law works because we maintain low pressure, right? PD and RT and KT, whatever. You can just plug in there. You can calculate. And you see that lambda indeed is proportional to the temperature, but also it's related with the size of the atom. It makes sense. And more than anything else,
inversely proportional to the pressure. So the more the pressure you have, the longer the mean free path you can maintain. So think about a typical atom, which is probably half of the nanometers, so 5 angstroms, you know. And KT is, this is the temperature value. At room temperature, you have this kind of number, you know. And you can easily calculate it because K is Boltzmann constant, the famous 1.602 times 10 to the minus 19 power, and you can easily calculate this energy level. And in that case, at 1 atm, right, the mean free path will be very short, 50 nanometer. Every 50 nanometer, these molecules will hit each other. Okay, it's like a cloud, it's like a gas. But if you maintain the vacuum at high level, 10 to the minus 7 total loop, the mean free path will be as long as 50 meters. In other words, this little particle of atom, metal atom, will travel 50 meters before it hits the other molecule. So this travel path will be super straight. That's the beauty of this deposition. Okay, so in order to achieve this high vacuum, which is less than 10 to the minus 7 torr range, you would mix mechanical pumping and different kind of pumping together. Why mechanical pumping is not going to work? Let's think about this thought experiment. You have a syringe with perfect sealing, okay? Perfect sealing. I say, just retract this syringe. There will be no molecule that penetrate through this sealing because it is perfect. Yet, if you maintain super high vacuum here, the matters, particles over the surface will start evaporate. That's why we call this super high vacuum a beast. We call this phenomena outgassing, and that occurs in the space. If you shoot a rocket into space, the surface coatings, the surface elements will easily evaporate into super high vacuum in the process called outgassing. Because like outgassing, you can never ever be able to maintain high vacuum. Okay? In that case, you have to remove all these little molecules by, for instance, here you can use either cold trap, let them get, let them get frozen, and then eliminate them. Or you can even use oil. This looks very messy, but it really works. You use clean oil, silicone oil, literally lick them down, okay? Just trap the gas, and then put them down, and then just pump them away. So you will really need a special technique in the case. Okay, so this is the typical real cross-section of a bell jar. You maintain the high vacuum. You use a mechanical vacuum pump first, and then switch to a diffusion pump or the other kind of pump as well, and then you can maintain high vacuum. So it takes a lot of time to create this high vacuum. Normally, somewhere between 30 to 1 hour. So when I did the clean room process for my PhD topic, so you turn on the vacuum pump inside the clean room. You just wear all these gowns and go into the clean room, prepare your wafer, put your wafer inside the bell jar, open it up, and turn on the vacuum. Takes like an hour from there. There's nothing to do inside the clean room, so I just came out and had the hamburger and played basketball, and then come back. Then the vacuum is ready, and we can turn on the deposition. Okay, that's very interesting experience. Well, there are some deposition characteristics you need to study. So basically, what happens is that if you have a source like this right here,
And as we learned, the path of travel will be very straight. So if you have this kind of structure, there will be shadow. So there will always be shadow effect. In order to avoid such kind of shadow effect, people have this kind of sun and planetary mechanism. Okay, so you put your wafer here, your source is here, your wafer, number of wafers, many wafers will turn around the source and equally exposing this shaded area. Okay, so that deposition becomes conformal in that case. But even though deposition is not conformal, even though deposition is totally shaded, you can use such characteristic for very special processing technique, which is called lift-off technique. So I'll talk about the lift-off techniques. The materials you can deposit could be almost anything. Well, aluminum, titanium, copper, chromium, gold, copper, platinum, silicon, whatever you can melt, even silicon dioxide. Even though the characteristic is not really good, you can deposit all kinds of material that you can melt with this vacuum technique. But compared to this, people can also use something called sputtering. Sputtering is a little different method. You would accelerate non-reacting gas and an ion, and then let it bombard over the surface of a metal. And as a consequence, this metal will actually be evaporated. But this event occurs at low pressure, not high vacuum. So that you are literally generating the cloud of these metals. This cloud of metals will be deposited. The result is more or less conformal compared with the electron gun, electron beam evaporation. It's called sputtering process. There are some good reasons why people use sputtering process in other cases. Sputtering yield, when one metal atom is generated by one argon ion, we call it the number of metal atoms that is generated by one argon ion is called sputtering yield. And you can even etch the surface with the sputtering. You have a wafer, just use argon atoms to bombard over the surface, to clean up the surface. That is also possible. The characteristic is a low vacuum, so 100 Pascal range. So mean prepath will be about 50 microns. So it's really the cloud, not the straight path of these metal atoms. So step coverage is good. Sometimes you want to have a very good step coverage. We'll talk about this, depending upon your goals. We can use either electron beam, electron gun evaporation, or the sputtering process. And you can maintain better contact, and the stiction is better. Argon gas is trapped. Well, this is sometimes good, the other times bad. Why? We'll talk about. This is the device. You have a cathode showed here. Your wafers are here. You will bombard, your wafers with the accelerated ions like argons, and your wafer will be deposited with these metals. So your argon will bombard over the target, and that will evaporate and then deposited on the surface of the wafer. Okay, and there are ways of calculating the resistance, and that's very simple. Resistance itself is defined by Ohm's law. Resistivity and the length of the conductor divided by the area of the conductor, in case you have a ideal line. Okay, and the length, area is nothing but, in this case, thin film. We are dealing with the thin film. Area is nothing but thickness times the width of this metal, right? So that instead of this definition, you can define the other way around. Resistivity divided by the thickness, we call it sheet resistance. And instead, you have a L, length, over the width. We call it aspect ratio. Okay? And the rho is the conductivity. Why can you calculate this conductivity like this? Well, sometimes this conductivity occurs with electrons, the other times holes. So the total conductivity will be addition of these two, and the sheet resistance with this definition can be calculated with this concept, this physically well modeled. So it will be also part of your homework, to try these kind of equations. So there are definition of all these parameters right here. Okay, I think time's up. And in case you want to measure resistivity, look here, you are calculating the L over W, 1, 2, 3, 4. That's the ratio, right? The aspect ratio. 4 times 50 is a sheet resistance you can measure with specific equipment. How can you measure? We'll see next time when you have a tour to the clean room. So this range resistance will be 200 ohms. Each end you consider 0.65 squares. Based on the simulation and experiments. So total will be 265 ohms. So this is the rough way of calculating total resistance using the concept of sheet resistance. Okay. I can stop here. Everybody, I hope everybody has a good weekend, and we'll see next Monday. Thank you.